So the next kind of flip-flop is the JK flip-flop. So what JK flip-flop is? As of now, we discussed about RS flip-flop, where we have a problem like indeterminate state is coming if S and R is equal to 1. Okay, at this state, we will get the forbidden state, and that is not acceptable at all. To avoid that problem, we come up with the D latch. Okay, but suppose if I want to make a counter, pulse counter, in that case, those kind of flip-flops like SR flip-flop or the D flip-flop will not solve the purpose. Okay, so to avoid that thing, we need to come up with a different structure that we call it the JK flip-flop. So see, in SR flip-flop we had 2 input. Okay, in D flip-flop we have only 1 input, but maybe we can have a 2 different set of inputs like 0 and 1 or 1 and 0 or set or reset. Okay, if I want to set the output, then you can activate it. If you want to reset the output, you can make it. But both are not possible in the D flip-flop. So to avoid that thing, we need to come up with one structure or one flip-flop that can avoid the indeterminate state, as well as that can have 2 inputs. Okay, so the JK flip-flop is nothing but that provides both kind of facilities. The first one is it has 2 inputs. The second one is it avoids the problem of indeterminate state, and the output is always toggling between 2 states. Like suppose we have already seen we can have a 4 like suppose if I have a 2 inputs. So in case of 2 inputs, I will have a 4 possibilities: 0 0 0 1 1 0 and 1 1. Okay, so if these are the possibilities, what it indicates, if you talk about the SR latch, okay, so if this is SR, then in SR latch Qn plus 1 is nothing but this is the for Qn it becomes the Qn. Qn plus 1 is nothing but this is the Qn for S is equal to 0 and R is equal to 0. For S is equal to 0 and 1, this becomes 0. For 1 0, this becomes 1, and for 1 1, this is the indeterminate state, which is not acceptable. So these are some of the states. Okay, and if you can recall here, these 2 states are giving a perfect output as per the requirement. Okay, but this state and this state are not that much important actually. So the first combination 0 0 is giving the past state only. So if I want to hold the data, in that case this combination is fine. But because we are designing the flip-flop, that itself can hold the data, it can store the data whatever we have. So this combination may not be that much useful. Okay, and the last combination, which is the 1 1, this is the indeterminate state, which is not acceptable. So we need to consider these 2 states. But if I'm talking about the JK flip-flop, the JK flip-flop will remove these problems, like a forbidden state kind of problem will be removed, and at each time the output, see what forbidden state means. It means that we are not able to predict what output we will get. Okay, if S and R is equal to 1, either it will set or it will reset. Okay, so to avoid that problem, to fix the output, like exact output either 0 or 1, that JK flip-flop is utilized. Okay, so the only benefit of the JK flip-flop is the state in the SR flip-flop, considering the 1 1, that was giving the forbidden state, which was not, we were not able to understand what kind of output I will get if I will provide S is equal to 0 and R is equal to 0, S is equal to 1 and R is equal to 1. Okay, but after considering the JK flip-flop, you will be able to understand what output I will get, either 0 or 1. It is predictable. We can predict it, what output I will get. So there will be no question mark, there will be no forbidden state, there will be a fixed output, either 0 or 1. Okay, so this is how we can remove the problem of SR flip-flop with the help of JK flip-flop. So let us try to see how we can avoid that problem with the help of JK. Okay, so the JK flip-flop, like suppose I just told you, the JK flip-flop looks like SR latch only, SR flip-flop only, with some modification. So what modification we need to do it? Okay, so let us try to see here. Yeah, so this is, if you can recall this one, this is nothing but this input was set, this input was reset, and this input, this was the clock. Okay, So this was the structure for SR flip-flop. Okay, this was the simple structure for SR flip-flop. Now, what modifications we need to do to make this circuit as a JK flip-flop? Okay, so let us try to see. To make it JK flip-flop, because if we can again make a feedback of this QN bar, like the output, complemented output with the set input and the original output with the reset input. Okay, so if we are able to make like this kind of arrangement, if we are able to connect like this, then we can avoid the problem of indeterminate state which was in the SR latch. Okay, so this is how we can avoid it. See, this J is nothing but this act as a set input, just like a S input in the SR latch, and this K act as a reset input. Okay, so these two inputs are similar to the set and reset inputs, but the forbidden state is avoided here. Just connecting this Q complement to the J input and the Q to the K input. Okay, so this is what we have to do the modification. Just these two lines need to be added. Okay, after adding these two lines, we will get a JK flip-flop. Now let's try to see whether it really able to avoid the forbidden state or indeterminate state. So let us try to validate it. Okay, so here we will get Q, Qt and Qt plus 1. So let us try to make the characteristics table, how the characteristics table looks like. Okay, so there are because see here, yeah, so let me write few things. If you see this point is nothing but here we have a J, here we have a clock, and here we have a K bar here. So if we can write, if I try to remove the clock, like it is clock dependent, of course, if the clock is high, then this is high. So this output, yeah, this node is nothing but this is the JQT bar. Okay, this is the JQT bar. Let me write it properly. JQT bar. Okay, I'm assuming that it is a clock is activated. If clock is 0, then it will be in the it will hold the previous data. Okay, but if it is active, then the output of first AND gate will be JQT bar. And if we talk about the second one is nothing but, yeah, if you see here, the QT is connected. So the QT is connected with the input. So this will become K into QT. Okay, so the K into QT will be the output of this one. Now let us try to make the characteristics table for this one. How the characteristics table will look like. Because if you see in the characteristics, the J input, K input, and the QT is the responsible. QT and the QT complement. I'm assuming that both are complementary in nature. So to make the characteristics table, we need three parameters. The first parameter is the J, second parameter is the K, and the third parameter is the QT. Okay, so that is why we have made the table considering the QT, J, and K. J is similar to the set, and the K is like a reset in the RS flip-flop. Okay, so let us try to make the table. So we can have a 8 possibilities with these 3 input variables, and that will be like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these all are the possibilities. Now let us try to see the output at each state. Okay, so let us consider the first state. In the first state, what outputs I will get? Okay, suppose Qt is equal to 0, J is equal to 0, K is equal to 0. So if it is like that, so the output Qt is going to be something like this here. See, if it is 0, so set we know that J Qt bar. Qt bar means what? because j is 0, so j qt bar will become 0, so this input will become 0. Okay, and similarly this will also become 0, so 0 and 0, because k is 0, qt is 0, j is 0, qt bar is 1, so 0 into 1, that will give you the 0, and 0 into 0, k is equal to 0, qt is equal to 0, that will give the r is equal to 0. So s and r both are 0, and if s and r both are 0, what it means? It means that it will hold the previous state whatever we have. Okay, so the output will be same like the previous state. So the previous state output was qt, so I will get the 0. Qt was 0, so I will get the 0. So qt complement by default, it will be 1. Okay, now let us try to see the other cases. If qt is equal to 0, j is equal to 0, and k is equal to 1. I just told you k is nothing but this is just like a reset kind of. Okay, this is just like a reset input. So what will happen? What I will get? If I calculate this first one, 0 into 1, that will give the set is equal to 0. This is perfectly fine. If we talk about k into qt, so the k into qt means k is equal to 1. Okay, k is equal to 1 here, and qt is equal to 0. So again, r will become 0. So if r is equal to 0, so set and reset both will be 0. So again, it will maintain the same logic like 0 and 1. Okay, now let us consider the third case. So I will discuss the first 4 cases, and the rest 4 cases you will be able to understand what is happening. Okay, so this is how the second case is working. Now let us talk about the third case. In the third case, what we are doing here, we are making qt is equal to 0. Okay, so the qt is equal to 0, so the qt bar will become 1. So 0 and 1 is fine here. Okay, so the qt, now what we are making, j is equal to 1. J is equal to 1 means what? We are making this j is equal to logic 1. This j becomes 1, and the k is 0. Okay, k is 0, what it means? This r will become 0, but because j and q bar t or qt bar is 1 1 both, so set will become logic 1. And if set will become logic 1, what it means? Output is going to be logic 1, because the set is at logic high. We know that if set is equal to 1, then the qt is 1. Okay, so what we will get? We will get qt plus 1 to the next state, that will be g1, and the qt complement will be 0. So 1 and 0, something like that. Now let's talk about the fourth case. If I'm considering the fourth case where we have provided qt is equal to 0, so the qt complement will become 1, and the qt here was like, because it is 0, and the q will become 1, so 1 into 0, that is going to give r is equal to 0, and here because j is equal to 1, q2 bar is equal to 1, so 1 into 1, that will give you the logic in output 1. S will become logic 1, so the qt will by default it will become 1, so that will hold the same logic, and that is going to be 1 and 0. Okay, so this is how it could be calculated. So similarly, you can calculate for other states as well, like whatever the state we have just considered here, like 1 0 0 1 0 1 and so on. And let us consider any other logic, like let me consider 1 1 1. What will happen in this case? Okay, and rest other you can prepare it. Okay, so let us consider for 1 1 1. If 1 1 1 means like the qt is going to be 1, qt is going to be 1, k is going to be 1. Okay, k is going to be 1, and here j is equal to 1, so this j is 1, and the q2 complement will become 0. Okay, so the 1 into 0, so set input will become 0. K and qt are 1 and 1. What it means? 1 and 1, that will give you the r is equal to 1. Okay, so if r is equal to 1, what it means? The output qt is going to be reset to 0, so that I will get 0, and by default the qt complement is opposite, so that will be 1. Okay, so now we see these two are the cases where j and k both are 1, and j and k both are 1, and still we are not getting the indeterminate state. We are getting some of the logic, some of the outputs. Okay, we are getting some of the perfect output. So this is the advantage of the SR latch over the advantage of JK flip-flop over the SR flip-flop. Okay, so similarly, you can also calculate for the other three cases, and those results will be something like 1, 0, and 1. Because see, if 1, 1, 0, 1 means the QT will become 1, and this J is 0, so this will become 0, and accordingly you will get 1 and 0 and 0. So something, so it will become like 0, 1, and 0. So this is how the truth table looks like. Okay, so if anyone has any doubt, then you can ask the question. Okay, so anyone has any doubt at any point of time? If you have any doubt, you can. Okay, fine. So this is how the characteristics table looks like. Now let us try to make a precise table, like how the output looks like. So if we can make the precise output, so if I have only two inputs, I'm considering only two inputs. So in that case, the total, I'm not considering the QT. Yeah, QT is by default, it is the one of the input, that because we have feedback gate. So if I try to make in terms of J and K only, so I can have a four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, now let us try to see what are those possibilities. One is this one. Like, yeah, let me change the color so that you will be able to understand. The first case is this one. If I'm considering the J is equal to 0, K is equal to 0, so I have two options. One is this one, and second one is this one. And in both the cases, either the QT can be 0 or it could be 1. Okay, so if it is like this, 0 and 0, so we can see here the QT plus 1 is 0 and the QT plus 1 is 1 for both the cases. And this 0 is nothing but this is same like a QT, and this one is nothing but this is the same like QT. So we can say that QT plus 1 is going to be same as the QT. Okay, so if we consider a 0, 0 case, so in that case I am getting QT plus 1, that is 0, and this 0 is same like a QT. And similarly, if I'm considering 0, 0, so QT was 1 and I was getting logic 1. So we can say that we are getting the QT plus 1, which is same as the QT. Now let us talk about the other two cases, other cases. Okay, other case is like if J is equal to 1 and K is equal to J is equal to 0 and K is equal to 1. So we have a two possibilities. One is this one and another one is this one. Now let us try to analyze. If 0 and 1 is there, so I'm getting QT plus 1, 0, and QT plus 1, 0 in the both the cases. It does not matter what the QT is. QT was 0 here and QT was 1 here, but in both the cases I was getting QT plus 1, 0. What it indicates? It simply indicates that we are resetting the output. Okay, it does not matter what was the QT before, either it was 0 or it was 1. But if J and K is equal to 0 and 1, then the QT plus 1 is going to be 0. So what it means that we will get 0 in both the cases. So here it means like the remark is it will hold a previous state. Okay, so the previous state will be hold, and here it is going to reset the output. Okay, so the reset will be there. And if we talk about the 1, 0 case, let us talk about the third case. So the output will be something like this one. See here, third case is 1, 0 and 1, 0. And now if we see, we are getting output QT plus 1 and 1 in both the cases. It does not matter what the QT was. So it means we are setting the output. So the QT plus 1 will be 1 in both the cases. Okay, so it means we are setting the output. We will set the output. Okay, now the next case is like 1, 1. In that case, let us try to see here. If we say 1 and 1, and the QT was 0, and I was getting 1, and if QT is equal to 1, I will get 0. What it means? It means that, yeah, this last combination is really very important. If j is equal to 1 and k is equal to 1, in that case, output qt is going to become 1 if the qt is 0, and the qt plus 1 becomes 0 if qt is equal to 1. What it means? It is complementing the output, whatever the result we had in the previous state, and if j and k both are at logic 1, the output will be complemented. If 0, then output qt plus 1 will become 1, and if 1, then it will become 0. So this will toggle between two states. Okay, so suppose if I have provided j and k is equal to 1 permanently, and then what it will do? At each clock state, if the qt will become 0, then in the next clock it will become 0. And because now the qt will become 0, now if the next clock comes, then it will become 1. So 0 1 0 1 0 1 kind of toggling will be there. So at the output we will get the toggled output. Okay, so so that is why this is how the jk flip-flop is important than the SR latch. Okay, so this kind of things can be utilized to count the pulses, clock pulses. So the number of clock pulses each time I will get, I can count how many clock pulses I have received, because at each time it is going to count, it is going to toggle from 0 to 1 and 1 to 0. So if there is toggling, if we are able to manage those things, like if we are able to monitor how much toggle, how many times the output is toggled, we can calculate how many times pulse was passed through this design or through this circuit. Okay, so this is the importance of this jk flip-flop. Okay, so if we talk about the 1 and 1 case, in that case, what was the state before that will be the complemented, so it will become kt bar. This is not the forbidden state, okay, or not the indeterminate state. So this is how we can call it the toggle state. Okay, and yeah, qt plus 1 complement will be opposite, like q2 complement 1 0 and qt. So this is how we can make the table. If you have any doubt on this at this on these any of the tables or any of the working, you can ask the questions. So
how will we calculate clock pulse? Can you say that again?
okay, so see here, if we see the last case, okay, so in the last case what we did here, let me change some. In the last case, which was like j is equal to 1 and k is equal to 1 here, and we have a two possibilities here. Okay, so the 1 and 1 was there. 1 means j and k both are 1, and the qt is equal to 0. If qt is equal to 0, I am getting qt bar, which is 1, and similarly if qt is equal to 1, I am getting qt bar, that is 0. So what it means, let us assume I have a flip-flop, jk flip-flop, something like this. J and k, these are the flip-flop, and this is the qt. Let us assume I'm not taking the qt bar. Let us assume j and k are connected to 1, logic 1 always. And now what I am doing here, I am just connecting one clock pulse, something like this. Okay, so let us assume in the first clock pulse qt was 0. Okay, now in the next clock pulse, once the next clock pulse will come, because the qt, like initially I am assuming that qt was 1, qt was 0. So once the clock pulse will come, the qt will become 0 to 1. It will change from its state from 0 to 1. So once the clock pulse will come, it will change state from 0 to 1. Then when the next clock pulse will come, again it will change the state from 1 to 0, and so on. 0 1 0 1 0 1 is will keep on moving. Okay, so if we are able to analyze how many times it toggled, how many times it flipped the logic, we can say how many times the clock pulse was like high. Okay, so to monitor, like based on the output, we can see how many times of clock pulse was come, like how many times the clock becomes logic high. So if it is like 10 times, so it will toggle for the 10 times. Okay, so the based on toggling, we can say how many clock pulses comes to this flip-flop. Okay, because at each clock pulse it will change its state. Okay, and if we are able to monitor how many times it toggles, how many times it changes, we can see how many clock pulse received at the JK flip-flop. Okay,
Yes, sir.
you got this, sir?
Yes, sir.
Okay, perfect. So this is how we can do that. Yeah, later on we will in detail we will see how we can design the counter, right? So don't worry, I will tell you about this toggling in more detail when I will talk about the counter designing. Okay, how to design the counter and how this toggling play a major role in the counter designing. We will see later on. Okay, so this is all about the JK flip-flop. Now let us try to simplify the some of the things based on the JK flip-flop. Okay, so let us try to make the characteristics equation, state diagram, and the excitation table for the JK flip-flop. So yeah, so this is what the table which we have already prepared in the last slide, right? So that is why I just took it as a reference so that I do not need to write it. So we know that if qt j and k are 0 0 0, so it will become 0 and so on. So we have given the output for all the possibilities for JK flip-flop. Based on these possibilities, let us try to make the k map for qt kt plus 1. So let us try to see how it will look like. Okay, so the k map is like qt and j and k are there. So simply if you can if we are able to fill the 0 and 1, how it will look like. So 0 0 1 1 1 0 1 and 0. Okay, so based on this table, the k map will look like this one. And if we try to make the pairing, how the pair will look like. The first pairing that we can make is this one, which is the possible pair. Okay, and the second one is we can make here this one and this one. So after making these two pairs, we are able to accommodate all the ones. Okay, and if we try to write the equation for this one, what equation we can get? The equation will like equation for qt plus 1, that is going to be q t plus 1. This is going to be from here. If we see this k will be rejected, j will be there, and qt will be there. Okay, so qt bar will be there. So j into qt complement, and if you see the second pair, from this second pair qt will come out, and the k complement will be there. Okay, because see here, if you see this and this one, so j will be cancelled out, but k complement will be there. So plus k complement into qt. So this is the output or the characteristics equation for JK flip-flop based on the characteristics table which we have drawn just now. Okay, so this is really a very important equation that is needed, especially during the counter designing, and we can call it the characteristic equation of the JK flip-flop. Okay, based on this characteristic equation and this table, if we try to make the state diagram, so how we can make the state diagram? See here, if you see, we have two possibilities for this qt. Okay, either it could be 0. Okay, so these are the 4 possibilities where we can get the qt is equal to 0, and 4 possibilities for 1, and accordingly qt plus 1 is going to change. Okay, so if we know all these things, let us try to make the state diagram for the JK flip-flop. Okay, so we can have a 2 state. Okay, the first state, like the state the qt could be 0, or the second possibility is like qt could be 1. Okay, so these are the 2 output possibilities, 0 and 1. Now let's consider the qt is equal to 0 and j is equal to 0 and k is equal to 0. In that case, I am getting t qt plus 1, again the same state. Okay, I will get the same state if the, yeah, let me change the color. If j is equal to 0, k is equal to 0. So the for this one, j is equal to 0 and k is equal to 0, I am getting the same state. Now let's talk about the second one. If qt is equal to 0 and j is equal to 0, k is equal to 1, again I am getting the same output. Okay, so the same state is valid for the another case, which is j is equal to 0 and k is equal to 1. Okay, so for these two cases, the qt plus 1 is going to be 0. Okay, now let us talk about the third case. If you see this one, qt was 1, j is equal to 1, k is equal to 0. In that case, qt plus 1 becomes 1. So we are going to change from 0 to 1, and the case will be j is equal to 1 and k is equal to 0. If this is the case, I will get the qt plus 1 1. Okay, next state could be the fourth one. Let us try to see this fourth one. If qt is equal to 0 and if both are 1 1, then again I will get from 0 to 1. So it will shift from 0 to 1. If j is equal to 1, k is equal to 1. So j is equal to 1 and k is equal to 1. For this case as well, I will get the same state change. Okay, now let us talk about other four cases. If you see here, if this qt is equal to 1, okay, and j is equal to 0 0 and k is equal to 0, in that case I am getting the same kind of output. So the same output I will get, and the condition will be j is equal to 0, k is equal to 0. Okay, so I will get the condition j is equal to 0, k is equal to 0. So for this case I will get the same output. In the next case, again I will get so if you see here, if the qt is equal to 1 and j is equal to 0, k is equal to 1, so I'm changing the state from 1 to 0. So 1 to 0 change will be there, and the case is j is equal to 0 and k is equal to 1. J is equal to 0 and k is equal to 1. Okay, now let's talk about the seventh case. Seventh case is this one, where the qt was 1, j is equal to, so it is maintaining the same state, and the case is j is equal to 1 and k is equal to 0. So it is maintaining the same case, and but j is equal to 1 and k is equal to 0. Okay, and if you talk about the last case, in the last case, if the qt is equal to 0, it is changing from 1, it is changing from 1 to 0 for this 1 1 case. So again it will become j is equal to 1 and k is equal to 1. So this is how the state diagram we can make for this jk flip-flop. So if you have any doubt at any point of time, you can ask the question. Okay, so yeah, based on this characteristics table only, we have just made this state diagram. Okay, so this is really important actually. So once we are ready with this state diagram, what other things we can make? We need to make the excitation table, because the excitation table is required, especially if I want to design a counter. So okay, so we'll use it later on when we'll design the counter, and I will tell you how much important the excitation table is. So excitation table depends on the past value, and accordingly we need to calculate the present value. Based on the past and present value, you need to calculate the input combinations. Okay, so let us try to see how the excitation table of JK flip-flop will look like. Okay, so I can have two output states, qt and the qt complement. Okay, and based on that I need to get the combination for set and reset. Okay, so let us try to see based on this state diagram. Again, I can have four possibilities for the these two outputs. Either the jk is 0, qt is 0 and qt plus 1 is 0. This is the first possibility. qt is 0 and qt plus 1 is changing to the second one. So the first possibility is this one, this loop which we are saying. 0 and 1 means from 0 to 1 we are changing this one, so I need to consider this loop. Okay, so let us do one by one, that will be better. So if I'm considering 0 and 1, 0 0, like the qt is 0 and qt plus 1 is again 0, so we are getting these two cases. These two cases are responsible for this one. And if we clearly see here, j is 0 for both the cases, but k can be anything, either it can be 0 or 1. So I need to keep j is equal to 0 and k as a don't care condition, because k both the combination for k that will give you the same state. Okay, so the k will be the don't care condition. This is the first case. Now let us talk about the second case. Okay, second case is my like qt is equal to 0 and qt plus 1 is equal to 1. What it means, we are considering this state. If we are considering this state, so let us try to see here. Here j is going to become 1 for both the possibilities. So the j is going to be 1, but k can be anything. So k, I need to keep it at don't care state. So the k is at don't care state. Okay, now let us try to see the third case. Third case is like 1 and 0. Okay, 1 and 0 means what? 1 and 0 means this one, 1 to 0. We are changing state from this to this. Okay, 1 and 0 means this one. And if we try to see this k, this combination, the k is at logic 1 and j is at the don't care state. J can be 0 or 1. So the j is at the don't care state and the k is 1. Okay, and the last possibility could be like qt is 1 and the qt plus 1 is again 1. So we are considering this loop or this state, and if you see closely over here, k is equal to 0 in both the possibilities, but j is going to be don't care. So j is at don't care state and k is at 0. So this is how we can get the excitation table for the jk flip-flop for all the four possibilities.